Okay, so let's begin the process of getting finite answers in quantum field theory for various observables. And as I had mentioned earlier, this procedure is called renormalization. Okay, so let me briefly summarize what we have done so far. So we have seen that the integrals diverge the moment you go to one loop. Okay, and we have also seen using dimensional regularization how exactly these divergences appear, these ultraviolet divergences appear in the theory. Okay, and we have seen that we get simple poles at one loop in 4 dimensions. As you approach 4 dimensions, you get simple poles. In epsilon, okay, where you take d equal to 4 minus 2 epsilon and let epsilon goes to 0. So now our next step is to build the dimensional continuation which we did for the integrals directly into the Feynman rules. Okay, that's what we want to do now. But none of this is going to solve any of our problems as such. But what it will do is it will make it easier to or more systematic to understand the singularities. Okay, what kind of singularities will appear in a more systematic manner rather than just looking at the individual Feynman diagrams. Okay, so that's what I want to do. And as I said, this is not going to make anything finite because I have to take epsilon going to 0 eventually, meaning I should work in 4 dimensions and all those integrals will diverge. Okay, but nevertheless, this will be the first step towards our goal of getting finite answers. Okay, so let's begin with that. So again, my all the work that I'll do will be in the 5-4 theory, whose action is this d4x half del mu phi minus half m square phi square minus lambda over 4 factorial phi to the 4. Okay, but now I want to use a different action, not this one, which will be given by this. So instead of working with this, this action, we work with the following. So I will work instead with integral d dx. Okay, I am going to d number of space-time dimensions. Okay, and you have again half del mu phi that will not change because after all this is what this is d0 phi plus d1 phi plus d2 phi and so forth. And if you have d number of them, let's say d is integer, then it is just have more number of terms, right? So it will have d0 phi d1 d2 and so forth up to d minus 1 phi d minus 1 phi. Okay, but I am going to view it not as a d as an integer, but I will let it even take fractional values. Okay, but we will not worry so much about what exactly it means to have d as fractional. Okay, and worry about those details. Our aim will be just to get Feynman rules which are valid and eventually which give integrals which are of this form. So instead of getting integrals of this form, I will start getting integrals directly of these forms, like these ones. Okay, here, which are already continued. So that's all we are trying right now. Okay, and I'm not trying to worry about what it means to have an action in fraction number of dimensions, okay, or even yeah. So let me write it as minus half. Instead of m, I will write m prime. So m prime square phi square minus lambda over 4 factorial, lambda prime over 4 factorial phi to the 4. Okay. I have just renamed m to m prime and lambda to lambda prime. Okay. Okay, so I want to work with this integral, and now this is in 4 dimensions. Instead of 4 dimensions, it is in d dimensions. So let's do the first simplest exercise of checking the mass dimensions of the fields and these mass parameter and the coupling constant that appear here. Okay, and remember, to do that, we should remember that S has dimensions of h bar or h, Planck's constant. Okay, they have the same dimension. If you check, look at action, okay, and convince yourself that action has mass dimensions of this constant h. If you have not already done so, then because we are in natural units in which h bar is 1, also c is 1, it means that because h bar is 1, a number, it's a dimensionless object, okay, in these units, then action is dimensionless, meaning the mass dimension of S is 0. Okay, it's m power 0. Okay, so now let's determine the mass dimension of m prime and lambda prime and phi. Now I cannot start that exercise from this term or this term, okay, because here there are two objects whose mass dimensions are not determined. I have phi, I don't know what's the mass dimension of that, okay, because now I'm in d dimension, the mass dimension of phi, what it used to be in 4 dimension, is not going to be true. And also in this term I have another factor m prime square, so I cannot disentangle from here the mass dimension of phi and mass dimension of m separately. Okay, so I should go to a term in which I do not have this issue, and which is this one, first term. Okay, there is only field phi for which I need to figure out the mass dimension, because the dimension of del mu is known. Del mu is just a derivative with respect to a particular coordinate, so that its dimension will be 1. So this I know. Okay, d dx, the mass dimension of that will be minus d, right, because you have dx 0, dx 1, dx 2, so and so forth, dx and d minus 1. Okay, so they are, each of them has a mass dimension of minus 1, so the total mass dimension will be minus d. Okay, so this has minus d, del mu has 1, so minus d plus, for this it is 1, for that it is 1, so 2, or 2 plus mass dimension of phi, but there are two such factors, so 2 times of it, and that all should add up to 0, because action is dimensionless, so each term should be dimensionless. So what does that give? That gives d is equal to, mass dimension of phi is equal to d minus 2 over 2. That is what in general case, but for us, because we are taking d equal to 4 minus 2 epsilon, okay, so 2 over 4 over 2 is 2 minus, yeah, correct, so 4 over 2 is 2 minus epsilon, and then you have minus 1 coming from here, minus 1, so this is 1 minus epsilon. Okay, so that's the mass dimension of phi. Let us now find out the mass dimension of m. So again the same exercise, m prime, this you will find that this is 1. Okay, let's check how. So mass dimension of phi, so phi square is here, so it will be d minus 2 over 2, okay, and sorry, d minus 2 because 2 factors, okay, so d minus 2 over 2 is for each phi, so 2 times of it, so it is d minus 2, and you have a minus d, okay, so let's write down there, d dx you have, and then you have m prime square, and then you have phi square, okay, so this is giving you d minus 2, that gives you minus d, and this is 2 times of m prime, and that should add up to 0, and you see that m prime has dimensions of mass, so it's 1, okay, from this m prime is 1, dimension of m prime is 1, okay, and let's now look at lambda prime. Remember, lambda prime or equivalently lambda in 4 dimension, it used to be dimensionless, okay. Let's see what happens when you go to d dimensions, whether lambda prime is still dimensionless, okay. So again d dx, so it gives you minus d plus lambda prime, dimension of lambda prime, plus phi to the 4, so 4 times d minus 2 over 2, okay, because each of phi has dimension d minus 2 over 2 from here, okay. So what does that give? This gives lambda prime 4d over 2 is 2d, 2d minus d is d, and this is minus 4, or lambda prime is equal to 4 minus d, okay. So as you see, this is correct, because if d is 4, then you get 4 minus 4 zeros, so lambda prime becomes dimensionless in 4 dimension, which is something you already knew, okay, and this in 4 minus 2 epsilon dimensions becomes 2 epsilon, okay. So lambda prime has dimensions 2 epsilon. Let me record all this here. Phi has dimension 1 minus epsilon, m prime has dimension 1, that didn't change from 4 dimension, it's still the same. Lambda prime has dimension 2 epsilon, okay. So what I will do now is I will redefine, I will just a second, I will redefine this lambda prime such that in this way, a lambda prime I will call it mu to the 2 epsilon times lambda, okay. So that's how I want to write lambda prime. So this is basically defining lambda. Mu is some arbitrary mass scale, okay. So what's the benefit? By doing this, lambda becomes dimensionless, right? Because if you look at the mass dimension of lambda prime, this says mass to the power 2 epsilon. So when you take it on the right hand side, the mass dimension of this, mass dimension of mu will be mu to the 2 epsilon will be 2 epsilon, and because now the mass dimension of left hand side is already taken care of by this the factor mu to the 2 epsilon, lambda is dimensionless, okay. And also note that mu is completely arbitrary. This has no relation with any of the physical scales in any problem, okay, which you are doing, because here the purpose of mu is just to absorb the mass dimension of lambda prime, okay, so that I can have lambda to be dimensionless. Also, I will, instead of calling m prime, I will call it m, okay. The reason I put m prime in the beginning, because I wanted to check what is the mass dimension, and if it also had it has changed its mass dimension, then I would have Similarly, introduce some scale, okay, mass scale, but because it turned out to be again having the same mass dimension as before, I'm not changing it. Okay, so so that's the notation I want to use now. So I will write these that action using these lambda and m. So my action becomes integral d dx half del mu phi minus half m square phi square minus mu to the 2 epsilon lambda over 4 factorial phi to the 4. Okay, that's the action with which I want to work. Okay, and remember, lambda is dimensionless now. Okay, so I will just write this here. Okay. Now, some time back, I think in the previous course probably, I had told you that we can redefine the fields. Okay, there is nothing secret about half del mu phi. Even the factor half here, right? This factor half, you could absorb into phi. You could say, I don't want to work with this phi, but I will define half phi to be, let's say, phi prime, and I will write this action as del mu phi prime, and that half factor will start appearing in these pieces. Okay, that is something you could do, and we also had introduced some factor of z and redefined. So what I'm going to do now is I'm going to redefine the fields and these parameters again. Okay, and you will see later why that will be useful, but for now I will do this. Okay, so let us define phi to be z phi to the half, okay, times phi r, and m to be zm times mr, and lambda to be z lambda times lambda r. Okay, where phi r, mr, and lambda are the fields which are finite, and these z's they are so zi, where I is phi, m, or lambda, is of this form: 1 plus let's call it zi prime. Okay, where zi prime starts at order lambda. Okay, so I'm saying that instead of working with phi, I want to work with phi r. Okay, and here is some change in the normalization of the field. Okay, I'm just changing the normalizations of the field and of these m's and lambdas, and I've introduced these factors. Okay, and I say that these factors are of this form: 1 plus zi prime. Okay, like zm is 1 plus zm prime, and where the property zm prime has is that it starts at order lambda. Okay, it doesn't have a order 1 term, it starts at order lambda. Okay, it will be lambda times something plus lambda square times something and so forth. Okay, so that's the redefinition I do, and these constants z phi, zm, and z lambda, these are called renormalization constants. Okay, and these z's are functions of lambda and m. Okay, and because lambda is a function of lambda r, okay, m is a function of lambda because there is a factor of zm. Zm depends on lambda and m, but lambda is a function of lambda r, m is a function of mr. So all these zi's are basically functions of lambda r and mr, right, because of these relations. Okay, an important point is that zi is 1 per plus order lambda r terms. Okay, so here I said zi prime starts at order lambda, but now because lambda itself starts at order lambda r, okay, because lambda r times z lambda and z lambda is 1 plus something. So this statement then becomes zi prime starts at order lambda r, okay, because of this relation. So all these renormalization constants are actually functions of lambda r and mr, okay, the way I have defined all this. So also another thing I should tell you, that the way I have written redefined these fields, you will see soon the nature of these z's, that they are going to absorb infinities, okay, and we'll see what all this means after we have done the calculation. Okay, it's easier to appreciate once the calculation has been done, when you have seen everything explicitly, then one understands why this has worked or what is the meaning of doing all this. Okay, beforehand it's a bit difficult to appreciate. So yeah, one thing I wanted to say here is that this is called multiplicative renormalization. Okay, when you have these couple renormalization constants multiplying the renormalized fields. Okay, when I'm using subscript r, okay, to a field or a parameter, I call it as a renormalized field. So phi r, mr and lambda r, these are renormalized fields and parameters, whether it's a mass parameter or a coupling constant. Okay, and this because this is multiplicative, the z factors are multiplying the phi r's, this is called multiplicative renormalization. Okay, I should have used some color to my, okay, so this is multiplicative renormalization. These are renormalization constants, and these fields and mass parameters, these are called renormalized fields and renormalized mass parameter and renormalized coupling constant. Okay, so good, I have said a lot of things here, but mostly it is just redefining something. Okay, now whether all this will be useful or not, we have to see later, but no one can stop me from doing what I have done just now. Okay, you cannot, there is no way you can stop me from saying that this is not allowed. You cannot say that I cannot write phi as z phi half times phi r, okay, because this is allowed. I can redefine the field. Similarly, mass parameter, I can write it as a product of these two, okay, where zm is some constant, okay, and z lambda is some constant. I can write it this way. Okay, so if you cannot stop, not because you are not physically present here to stop me, but because there is nothing inconsistent that I am doing, so I am allowed to do this. Okay, so let me put this back into the action and see how the action looks like. Okay, but it's still the same action. Okay, this action, I'm not going to change anything. It's the same action, I rewrite differently. Okay, so as the action becomes the same action the same theory now looks like the following. Half z phi to the half times phi r, del mu phi r. Okay, again there is a del mu phi r, and that also brings a factor of root z, square root of z, and those two square roots of z make z phi. Okay, so that's first term. Then you have the mass term, and that becomes minus half. We had m square, so, and also phi r square. So phi square. So phi r, phi, when I write in terms of phi r, it becomes phi r square, and it will bring a factor of z phi. Okay, so that is what I am writing here. Then you have m square, and when you write it in terms of m r square, it will bring a factor of z m square. Okay, because zm times mr is what is m. So the square of it gives you zm square mr square. Okay, then you have minus minus 1 over 4 factorial. Let's stop writing now. Mu to the 2 epsilon. Okay, then you can check that you get z lambda. It's not writing why. Z lambda times z phi square times lambda r times phi r to the 4. Okay, let's check whether this is correct. Because you had phi to the 4, okay, it will bring 4 powers of square root of z phi, that makes z square, and then we had lambda here, and that brings z lambda, and this is mu to the 2 epsilon which was present, and minus 1 over 4 factorial. Okay, so that is how the action looks like now for the same theory. The physical content has not been changed. Okay, it's all the same. I have just redefined fields, but that doesn't change the content of the theory. Meaning, if you were calculating some observable earlier using S, and you do it again, you will get the same result. The only thing is that earlier you were getting nothing because you were getting infinities, and now also it's the same. So you still don't get anything sensible, but as far as the theory is concerned, it's the same theory. Okay, so now this does not look like what we are used to. So I will now add and subtract the following to this action. Okay, add and subtract the same thing so that I don't alter the action. So add and subtract half del mu phi r minus half mr square phi r square. Okay, so this is something in terms of the renormalized fields and renormalized mass parameter. Okay, so I will just add and subtract this to the Lagrangian density, and my action will become the following. So S is integral d dx. So I am adding now first half del mu phi r minus half mr square phi r square. Okay, now I should subtract this from this action, right? So that it means that I have not done anything, I have not altered anything in the action. So when I do so, I will get the following terms. So I will write this half z phi del mu phi r and subtract from it half del mu phi r. which will give me half Z phi, so that is the term which is present, and from when I am subtracting this gives a minus 1 del mu phi, it's not, del mu phi, the laptop has slowed down suddenly. Why? Okay, anyway. Okay, let's check whether this is correct. So you have here, if you take this first term and this term and add them up, what do you get? Because of this minus 1, this term cancels. Okay, and you are left with only half Z phi del mu phi r, which is what you had originally. Okay, which means that I have not changed the first term as I have written here. Okay, now let's look at minus half m r square phi r square term that I have added. So I should subtract it, and I will subtract it from here. So minus half, okay, looks like cannot write at all, minus half let me try again, Z phi Zm square minus 1, okay, m r square. I just want to finish this action, it's not letting me. M r square phi r square. Okay, so let's check whether this is fine. Again, minus half times minus 1 is half, so half m r square phi r square, okay, with the plus sign that cancels against this one. Okay, so that I get rid of, and what is left with this? What is left is half Z phi Zm square, half Z phi Zm square with the minus sign, m r square phi r square. So that is also correct. Now let me write down the last term, minus mu to the 2 epsilon okay, then you have lambda r over 4 factorial. What happened suddenly? Or 4 factorial, and then z of lambda, z of phi square minus 1. You can check that this is the right factor, and phi r to the 4. This is difficult. Oh my goodness. Okay, so finally I managed to write this. Okay, so that is how the same action which I wrote earlier in terms of phi's looks like when I write in terms of phi r. Okay, now let me tell you why I have done this before I proceed further, and anyway I cannot proceed further in this video because I am unable to write at all. So see the way it was written here in this on the top here. Okay, now it works. Okay, this is working now. Something I should close. Okay, so the way it was written here in the way the action was written on the top had del mu phi r, that's the usual kinetic term, but then you have a z phi. But z phi is a function of lambda r and mr, which are your constants. Okay, so I don't want to put it this way, but I want to put it in the canonical form, the way usually we write the kinetic term without coupling constants. Okay, and that's why I have written it this way, because once I write it this way, the propagator in the theory will be exactly the same which I had earlier. Okay, instead of m I will have mr, but other than that everything looks the same. So that's why I have added and subtracted that term, so that I in the action I have the parts for the free part, the parts which were present earlier. Okay, I think I missed this one. So not only add and subtract this, I also wanted to add this one. This one I forgot. Okay, so you see that I have added and subtracted the entire action that we used to have. The only difference is that instead of phi I have phi r, but it looks exactly the same. Okay, so here also okay, which is good, because when I am writing the Feynman rules, I will have exactly the same Feynman rules, with the only difference being that the names would have changed for the parameters, and mu to the 2 epsilon will appear in the vertex. But other than that, everything is the same. And there is another difference that will come here is you have more terms, so you have more vertices. Okay, let's look at this this term. Okay, this has z phi. Z phi starts with 1. So that 1 cancels 1, and it is left with z phi prime, which I had earlier defined, okay, which starts at lambda or lambda r. So this term would contain a factor of lambda. So that's a coupling term, right? This is a kinetic term. Here it does not contain any factors of coupling, but here it does. So that's a coupling term. That's a interaction term. Okay, which has derivatives here, but it's still an interaction term. Similarly, this one, okay, this is also quadratic like this one, this term, but again it contains factors of coupling, okay, coupling constant lambda r, and that is why this is also an interaction term, and the same is true for this one also, okay, because you have factors of lambda, and anyway this is not even quadratic, that is quartic, so that's also a coupling term. Okay, so compared to the theory written in terms of phi and m and lambda, this has more number of vertices in the theory, okay, more number of interaction terms in the theory. So now I will give you the Feynman rules, and you can immediately see that these are the correct ones. So let's write down the propagator. Maybe I should, okay, let me take it to the next page. Toolbar. Command C, and what happened? Okay. No. Okay. Okay, here, and then here I will just paste it. I hope that this will be also easily visible. Okay. So that's how the action looks like now. Okay. So what are the Feynman rules then? Feynman rules, or maybe okay, now I cannot move it. So Feynman rules. Remember, it's still the same theory. I haven't changed really anything. Okay, physics, physical content, everything is the same. Redefining certain things cannot change the physics content. So how about the propagator? Okay. Propagator is given by these first two quadratic terms, and this is of exactly the same form as before, so I also get the same thing as before, but now it will be mr square. Okay, and remember, mr is still a mass parameter. Okay, it's not a physical mass of anything, because you remember how we find the physical mass of particles in a theory. You can look at the poles of Green's functions, or let's say 2-point function, okay, and look at the pole, and that pole will give you the physical mass. That physical mass will be a function of lambda and lambda and m, which in our case now have become functions of mr and lambda r. So physical mass will be a function of mr and lambda r. Okay, so MP's physical mass will be some function of mr and lambda r. Okay, that is what we can say, but mr is not itself the physical mass. Okay, so that's one of the Feynman rules. Then, as before, we have this vertex coming from minus lambda r over 4 factorial, phi to the r, but you have a factor of mu to the 2 epsilon also. And remember, recall that the vertex here was minus I lambda over 4 factorial earlier. That is what we had, minus I lambda over 4 factorial. So instead of lambda, I will have lambda r. Okay, and I also have factor of mu to the 2 epsilon. Okay, which is basically I times minus lambda r over 4 factorial mu to the 2 epsilon. Okay, so you see that minus lambda r over 4 factorial is this minus lambda r over 4 factorial, and there is a factor of phi. Okay, if you go back to the first course, you will see how this factor of I came out. Okay, in the Green's functions, because we had written everything in terms of how to say, vacuum expectation values of fields, and then there was an exponential, and e to the I of that interaction term, and that is from where the I was coming. Okay, when you expand the exponential, so it is that I. But now, unlike the fact that you had only this term in the expression of Green's function, okay, you also have these terms. Okay, so which means that these will also give you vertices. So let's look at these two terms now. There are two terms in this line, so let's take both of them. And del mu phi r, that will give you a factor of p square. Okay, when you take the derivatives, it pulls out factors of IP. Okay, so you will get the following. So this vertex, I am drawing it this way because it has only two fields, phi's, that appear, phi r and phi r. Okay, and so it has two external lines. This one also has phi square, so two external lines. Okay, and you get I times half z phi minus 1 p square minus half z phi Zm square minus 1 mr square. Let me check. Okay, looks fine. Now Z5 Zm square minus 1 mr square. Okay, so you see you have in this theory, I mean it's the same theory, but the way we have rewritten things, you also have a vertex which is a 2-point vertex. Okay, we never had such a vertex before. We always had a 4-point or a 3-point vertex, but it's the first time we are seeing a 2-point vertex, and these are usually denoted by putting a cross. Okay, so all those vertices in this action which carry a factors of z, okay, or zm or whatever, they will be denoted by this cross, by putting a cross on the vertex. And there is one more that you have, which is a 4-point vertex coming from this last line. Okay, and I put a cross because this also has factors of z's, and that's a 4-point vertex because you have 4 fields. Okay, so four lines you can connect, that's why it has 4 legs. So this is e to the I minus I times 2 epsilon lambda r over 4 factorial times z lambda z phi square minus 1. Okay, so these are our Feynman rules with which we should work. And remember, we always have momentum conservation at each vertex when we are drawing Feynman diagrams, and that momentum conservation is now d-dimensional. Okay, so it's really 2 pi to the d and delta d and the sum of all momenta that are entering into that vortex. Okay, so that's the only other thing that you have to keep in mind. Now, given that we have these Feynman rules, let's first figure out whether these these 2 new vertices, they are of the same order as the 4-point vertex here, or are they different? So this vertex is of order lambda r. Okay, so how do I do that? So this vertex is of order lambda r. Okay, now let's look at this one. This vertex has z phi and this term. Let's look at z phi. So z phi is 1 plus z prime phi, okay, or whatever, 1 plus some function that starts at order lambda r. So that one cancels, and whatever you have here starts at order lambda r. Okay, so this 2-point function clearly starts at order lambda r. This 2-point vertex, not 2-point function. So this is also a vertex that is of order lambda r. Now let's look at this 4-point vertex which we have in this way of writing. Here it already has an explicit factor of lambda r, right? Because you have a factor of lambda r here. Then z lambda and z phi, they start at order 1. So z lambda z phi square, the lowest order term in this will be 1. So that 1 will cancel this one. Okay, and the second term, the next term in these will be of order lambda r. Okay, so you see that this factor contributes something of order lambda r. Okay, that order lambda r term times this lambda r makes this vertex order lambda square, order lambda r square. Okay, so this is a vertex that is of higher order compared to these 2 vertices. So if you are calculating something only up to order lambda r, then you don't need to use this last vertex because that contributes at order lambda r square. Okay, so one has to be also careful in using this because these are of different orders. Okay, now we have all these Feynman rules, and we have modified or redefine the fields in terms of renormalized fields and renormalized mass parameter and renormalized coupling constant. Okay, but nothing has really changed. You still calculate whatever you want, you will get infinity. Okay, because just redefining things cannot help. So we'll see how to get finite answers in the next video. But here I want to also bring your attention to the fact that even though you have several interaction terms in this section, like this phi to the 4 term and this interaction term which has del mu phi r coupling, and this phi r square and phi r 4, these coupling constants are not independent. Okay, they are not all different, right? They are not all independent. They all are completely determined in terms of lambda r and mr. Okay. So because long back I was telling that whenever you write a interaction term in the Lagrangian, you have to include a coupling constant, and these coupling constants are independent of each other in general. Unless certain symmetries force them to be related, they are independent. And here you see that it is just because we have rewritten things in certain way, that is why these couplings are still given by these two coupling constants lambda r and mr. The number of coupling constants has not changed. Okay, it's the same theory. Okay, so all this algebra will be very useful. All this calculation will be very useful now in setting up the procedure to get finite answers. Okay, and that is what we will take up next.